Okay, now we want to have a look at this thing called small angle approximations, which is something we very commonly do. Approximations are all over the place in maths and physics, because in reality, the universe and maths in general is really hard. We want to make it a bit easier. So we throw in a load of these approximations. And this one, the small angle approximation, is pretty useful when dealing with unwieldy trig equations. So what I want to draw your attention to is to start with a sine and a tan graph. Now, ideally, if I was in a classroom, I'd be using a projector with Desmos on it, but we don't have the budget for that here. I do have a projector, but I don't have it synced up for the board. I don't think a camera would take it, and who's got time for that? So I'll have to make a do here, but please, if you want to go onto Desmos and visualize all this yourself, I highly recommend it. Let's first have a look at this y equals sine x graph. Now, you might notice that we are calling these small angle approximations. And that is because we are keeping all of these to only when angles are very, very small. So I'm going to restrict it to, say, this part of the graph. Very, very close to the origin. Remember, the angles are going this way, so very, very close here. If I look at this poorly drawn sine graph, or if I look on Desmos, what I notice is that inside this boundary here, this almost looks like a straight line, just drawn underneath it. Almost. If we zoomed in, we would see it was a little bit curvy. But the closer and closer we get to the origin, the more and more this looks like a perfectly straight line through the origin, or a y equals x graph. So, as we get closer and closer to the origin, as our angles become small, our sine x graph looks almost like an x graph. So we can say at small angles, sine x can be approximated as x. So if you ever see the word small angle, it is telling us that we are free to assume that sine x is simply just x. Get rid of the sine completely. Similarly with the tan x graph. Now, tan x is a little harder to see, especially on my diagram, because it looks awful, but I'm going to draw my boundaries very, very close. Hopefully you can still see that. But the point is, if I were to zoom in on, and I will kind of draw, that's what a tan graph looks like. If my origin is here, as I zoom in further and further and further, once again, it starts looking like a straight line. Now, of course, it's not a straight line. It does have a bit of curve, but the further in I zoom next to the origin, the, not steeper, but the less and less this curve becomes apparent. And we end up with something that just looks like a straight line, which is a y equals x graph. So tan x can also be approximated when the angle is small, when we're close to the origin, as x. Now, hopefully you can notice that in both cases, the further and further away from the origin we get, I mean, this is no longer a straight line, right? Over here, we do not have a y equals x line. So as our angles get into, 30, 40, even 10, 20 degrees, it just doesn't work. In general, it works best when we're under, maybe 1, but even at around 1, 2, 3 degrees, or if you want it in radians, whatever pi over 180 is, throw that into a calculator for fun, radians away from the origin. So very, very small numbers. But again, if you're doing this as part of an exam series, the word small is going to be there to help you. Because as we get really far away, I mean, this just quite simply is not a y equals x graph. Now, you probably noticed there's one missing from here. We haven't done cos yet. That's because cos, it's not quite as simple, but it's still the same idea. So let's have a look. Okay, here's my cos graph, or rather a very small part of the cos graph. The rest of it isn't really relevant. So once again, we're working with a small angle approximation. So the same as with sine and tan, I'm going to look very, very closely to my origin. Left and right, either side of the origin, what does my graph look like? Well, the eagle eyes amongst you have probably spotted we're nowhere near a y equals x graph, like we were with sine and tan. Instead, we have a different equation that fits this. And the graph of it looks like that. Again, over here, I mean, they're not even remotely the same, which is why it's small angle. But here, even on my rubbish diagram, you can still kind of see they're the same. Now, this line here has equation y equals 1 minus x squared over 2. You don't need to know the derivation of that if you want to, go nuts, but all you need to know is 1 minus x squared over 2 is this red curve here, which fits my cos graph very, very close to the origin. So at small angles, sine x becomes just x, tan x becomes just x, but cos x becomes 1 minus x squared over 2. Still more useful. It's easier to do algebra with this versus cos, but obviously not as great as a sine or a tan. Okay, let's have a look at this example here of a horrible looking sine tan cos equation with all three. And if this was a question, we would be told that we are working with small angles. So what can we approximate this by? So first of all, let's remind ourselves what our small angles are. Sine x is basically x, tan x is also basically x, and cos x, the weird one, trying to be different, is 1 minus x squared over 2. So let's break this apart. Sine of 5 theta. Well, always compare, especially in trigonometry, what's going on inside my function. Here there's a 5 theta. Here there's an x. So instead of having sine of x, I've got sine of 5 theta. So my x is equal to 5 theta. And what does sine x approximate to? It just approximates to x. So this thing here just approximates to 5 theta. Tan of 2 theta. Once again, what have I got going on inside here? 2 theta. What have I got here? An x. So x equals 2 theta. What do we know about the approximation of tan? Tan x is approximately equal to x. That's what these squiggles are, by the way. Don't know if I made that clear. I'm not just having a stroke when I write. These squiggles do mean approximately equal to, not equal to. Well, if x is 2 theta, tan of 2 theta is approximately equal to 2 theta. And then we've got cos. Well, cos of 2 theta, once again, my x is 2 theta. So if I look at this equation, this is where you've got to be careful. I'm replacing my x with my 2 theta. So now I've got 1 minus 2 theta all squared. Don't forget the squared goes outside all of it, including the 2 over 2, which is 1 minus 2 squared theta squared, so 4 theta squared over 2, or 1 minus 2 theta squared, cancelling a 2. So my cos of 2 theta is 1 minus 2 theta squared. Putting this all together, making sure I flip these signs properly, I get 5 theta plus 2 theta is 7 theta, minus 1 minus, so plus 2 theta squared. And out of this, I've got a much simpler equation just involving theta that I can probably solve quadratically and get my values.